Welcome. Let's talk about storage in database systems. Now, last time we covered buffer pools, and that's the project that you're working on now. And this is for when we have a disk-oriented database system, that is a database system which is storing its data on disk, and refer to the discussion of storage hierarchy from last time to see how disk fits in to the different places that we can store data. But our idea here is that we have a database that wants to be able to support storing more data than fits in the physical memory available to the system. And so all the data is going to live in a non-volatile, persistent location that is on disk, and the parts of it that we currently need to work with will be brought into memory. So because reading and writing from disk is much slower than memory, we want to try and, the database system is going to do a lot of work, have a lot of different techniques for trying to minimize the kind of amount of time different operations spend waiting for the disk. And for this reason, the database system is going to want to take a lot of control over what's happening with the disk. So if you have taken 208 in the last couple years, or an operating systems class, you may be familiar with the term virtual memory. And this is the idea that the operating system provides the illusion to programs, to running programs, that they have a kind of massive and uniform address space, set of memory addresses available to them, and it's the same for everyone. And of course the reality, messy reality underneath, is that physical memory is being shared and kind of divvied up among all these different processes. But this brings up the question: if we have an operating system functionality in virtual memory that is in fact already designed to do this management of providing kind of more the illusion of more memory than perhaps exists physically in the system, and that does transfer, have facility to have data backed by disk to transfer data to and from disk as we need it, why would our database system want to do this itself? Why couldn't we just use this virtual memory, these operating system functions in our database? And it's possible to give the operating system hints about what we want it to do with pages of memory. There's madvise to tell the OS what we're planning on reading. There's mlock to prevent the OS from swapping out a range of memory to disk. So this is basically pin a range of memory. And there's also msync, where we can flush a range of memory. Flush here meaning a kind of you're writing that memory out to disk and getting kind of any modifications that have been made to it in memory out there. But even though there are these ways to kind of guide the operating system and how to manage memory, it's still the case that the operating system doesn't know anything about the queries we're executing. And when the operating system doesn't know anything, it may just do things that interfere, that are harmful, that are the wrong decision for what our database wants to do. And because the database system knows what queries are running, knows what data they're going to need, it can almost always make better decisions than the operating system is going to. And so the database system almost always wants to control these things itself. Control when we keep stuff in memory. Control when we write out things to memory. Control when we might fetch data ahead of time from when we're going to need it. And so, yes, it's more work that the database system has to do, but we are going to have it, in almost all cases, the database system is going to kind of implement this whole kind of management of disk and memory itself. And so an operating system will have both the buffer pool manager that we've talked about, as well as a storage manager component. And our storage manager component is going to be responsible for kind of what file structure is used to store the database, how things are written and retrieved from those files, how to find files that we need, that sort of thing. And so this is kind of the piece that we're talking about in this video. How is the database actually kind of organizing its data on the disk? How is the storage piece working? So a fundamental unit of storage, and indeed the unit that the buffer pool manager brings in and out of memory, is a page. And this is a fixed size kind of chunk or block of data. And these pages, so we're going to have data is chunked into pages. And these pages may have different things in them. We might have tuples, we might have indexes, which is a topic we'll get into next week. But structures to make finding data and queries more efficient. We might have other metadata. We'll see some examples of that today. But these kind of all the stuff that the database needs to keep track of will be in pages, and we will rarely, if ever, mix these things together within a single page. So a page will consist of be a page of tuples, or a page for an index, or a page with metadata, and we won't mix them together. On a computer system, there are kind of different pages, different kind of subsystems within that use this idea of pages. And so in this case, we want to think about hardware pages. And these are the kind of chunks, the pages or blocks defined by the actual storage device, like the solid state drive or the hard disk drive. Will have a page size that it works with, and these are usually 4 kilobytes in size. We'll also have the operating system will have its pages, also usually 4 kilobytes, and then kind of the province of the database system will have its own pages that it's working with. So the operating system will have pages that it is the kind of chunks of memory that it is managing. The disk, the hardware will have pages, and database pages will actually range considerably in size, from at the small end something like 512 bytes. This would be like you have a SQLite database running on an embedded device, so you have kind of small amounts, relatively small amount of memory that's available, and you have pretty small pages, all the way up to 16 kilobytes, where the database actually uses these very large pages. And one important consideration is that the hardware page size determines kind of the guaranteed or atomic writes. And atomic is a word that will come up in other contexts as well. And the idea is an atomic operation, either all of it happens or none of it does. That it's kind of an indivisible unit of an operation. And so whatever size the hardware page is, that's the amount of data that the disk will be able to kind of write atomically, meaning that if there's a crash while the disk is writing, we won't end up with some kind of partial hardware page written and be in some kind of inconsistent state. Because the write is atomic, it will be kind of staged and processed such that it will all have happened or none of it will happen. And that's a desirable property when we want to provide functionality like recovery from a crash. We don't want to have our data be a huge mess if the computer catches on fire and the disk starts melting. But if we have hardware pages that give 4 kilobytes of atomic writes, and we have something like MySQL, which uses 16 kilobyte pages, we have this issue where now when the database wants to write out a page, it can't rely on the hardware to kind of provide some atomic write operation of the size of the page. And so the database will need to do extra work in order to be resilient to crashes, in order to kind of make its writes still have this atomic property, even though the hardware doesn't provide it. And you may ask, well, why would a database want to have this larger page size then? Well, if we have a larger page, we get kind of more efficient reads, because you may remember from talking about the storage hierarchy that sequential reads on disk are where they perform the best. And so if we have larger page, we get more sequential reads, and also when we bring a database page from disk into memory, we're kind of getting a bigger chunk of memory, so we might have better locality. We kind of get more of the data we're going to need in the near future. So there are some performance advantages to increasing the page size, but it involves extra work to make sure that the hardware that we have atomic writes. So we have these pages in the database, but how would we actually organize them within the database? So you've seen with SQLite in the homework that you're working on, that is just a single file for the database. You downloaded a DB file, kind of everything is in there. Most other database systems will split up the data across multiple files. But in either case, we need some way to find kind of where a page is within the files of the database. So whether we have one file or many, it's going to be the case that a given file might contain a bunch of pages, and we need to know kind of where to find them. So kind of the most common way that this is done is with what's called heap file organization, and this word heap here does not mean like a binary heap, a tree structure. It just means a kind of a pile of stuff, because our heap file is an unordered collection of pages, and our tuples within those will be an arbitrary order. And this arbitrary order of tuples piece is one to make adding new tuples and kind of maintaining these pages simple and efficient by not kind of requiring that we find exactly one place or we keep tuples in a particular order, and also because our relational model doesn't impose an ordering on the tuples. There's nothing requiring, for example, that tuples be stored in the order that we inserted them. The database is free to store them in kind of any arbitrary order that it wants, and the kind of within this heap file, in order to find where, say, a given page is, we have a page directory, which is going to basically be a hash table that maintains for each page information about that page, such as like how much free space it has, where it's located within our heap file or heap files. And so if we have like page 0, page 1, all the way up to page n, and each of these entries in our page directory will tell us where to find a specific page within our database kind of file structure, and this page directory itself will be in its own page, and like the page directory will be something that the database kind of always keeps in memory, because it's going to be needing kind of every time it needs to go get a page, the storage manager looks up in the page directory where to find that. Page directory would keep track of the free space available in each page, because when we want to add tuples, say, we would want to be able to find a page that has room by scanning through the page directory, rather than having to go to all the different places on disk with all the different pages. If we have in memory the page directory with the amount of free space that each has, we can just go and look that up. So this is kind of how we'll keep track of where the pages are on the disk. So let's dive into what is actually inside each of these pages. How is it keeping track of the tuples or what other data it has? And so our pages talk about how they're going to be laid out. So one thing that we're going to have in every page is some sort of header. And this header is going to record the metadata about this specific page. And it will include the page size, how much total space. It will usually include something called a checksum, which is basically a hash function of some kind applied to the contents of the page, and this lets us tell do the contents of the page kind of match what the header thinks it is when we want to recover from a crash. Was data corrupted within the page? We can compare the recorded checksum to the checksum of the current contents. And like hash functions, checksums are going to differ even with small changes to the input data. So they're a very common sort of data integrity tool. And another important piece of information we're going to record in the header is the database version. And this is because this sort of internal structure to the database could be changed through different versions, like SQLite or Postgres. As different versions of the database system come out, they may change kind of how what's in the header, or how things are structured, or other implementation details. And so when you're looking at a page, you probably need to know, oh, was this created by which version of the database software created this page, because that's going to influence how you need to actually interpret the bytes that are stored there. And so you'd have kind of branching code to handle the different versions. And so one sort of too simple approach to storing to our page layout in practice would be we have fixed size tuples, and we're just going to store them kind of one after the other. So we have our header, and then we would have our tuple number 1, tuple number 2, and so on as we fill up the page. And this is okay if our tuples are of fixed length. Every tuple is the same number of bytes, but if we have tuples of variable length, which we might commonly have in particular are tuples with strings. The strings might be different lengths, and we could just kind of pad out everything to be some maximum size to make all the tuples the same length, but then we're wasting space. And the other issue that arises is if we have our tuples laid out like this, and then we say delete a tuple from the database, then we kind of have this hole in our page, and then we could kind of reuse that if we insert another tuple number 4, but we don't kind of have any structure to this that tells us where to find a specific tuple we're looking for. And so we'd have to kind of, we wouldn't be able to rely that they're in a kind of the particular order that they were inserted. If we want to reuse empty space, if we leave it empty, then we're wasting space. If we kind of keep resorting everything when we insert, that's very expensive. So this is not going to be what databases actually do. The most common approach is to do what's called a slotted page approach, and this is kind of a tuple-oriented way of laying out these pages. The kind of the individual tuples are kind of what the main objective is, and what it's going to be is that after our header, we're going to have what's called a slot array. Looks something like this, and this slot array will get bigger. It will grow kind of from the top of the page down, and this slot array is going to contain pointers to the actual tuples in our page, and those tuples are going to be stored from the end of the page toward the beginning. So, and this will accommodate variable length tuples. So we're going to have tuple 1, and then tuple 2, tuple 3 here, tuple 4 here, and then we'll have in our slots, each will have a pointer to where that tuple is stored within the page. So let me actually use a different color so it's a little easier to see on the whiteboard. All right, and so these slots will have pointers to where the various tuples start in the page. So first slot tells us where tuple 1 starts, second slot is a pointer to where tuple 2 starts, and so on. And in our header, now we can also keep track of the number of used slots, the number of tuples that we have in our referred to by our slot array, and the last used slot, so we know where we would jump to in order to kind of the slot for an if we wanted to add a new tuple, we keep track of the last used slot so that we could jump there. We could see where the last tuple is currently stored, so we insert our new tuple before that in the page, and we know that the next slot is where the next pointer would go. And the way this works is that the tuples grow from the end of the page toward the beginning, and kind of when the slot and the array tuples kind of meet in the middle, that is when the page will be full. And this solves our kind of variable length tuple problem, because our slot array can just tell us where to start. And different database systems will handle deletes and reorganizing the tuples differently. Some, if we deleted tuple 3 here, it would just leave an empty space, and there might be kind of a particular value that the slot array would have, or some indication in the header of kind of which slots are currently free. Other systems, you delete a tuple, it would immediately kind of reorganize, kind of move tuple 4 over in the slot array, and probably over in the tuples here. And I'll link in the video description a nice demo from Andy Pavlo showing how different systems like Oracle, Postgres, and so on organize tuples, and also showing how they label them internally in order to be able to find them. All right, but this is our slotted page, most common approach. There is an alternative approach that kind of takes a very different view of the situation. That's not tuple oriented, but is log oriented. And so this is our log structured page. And here, instead of storing tuples in our pages, we're actually going to store log entries. And by this, what I mean is that each time some tuple is inserted or modified or deleted, a log entry to that effect goes into our page. And so we might have an entry like insert a record where ID is 1 and val is A, and then another log entry where we inserted another tuple, ID is 2, val is B, and then maybe we are deleting some tuple that we inserted earlier where ID was 4. We might have kind of something updating the value of these tuples. And in this case, kind of when we have new entries in our log, new operations, those kind of go, we're kind of appending them to our log pages. And when we want to read the data in our database, that actually will read the log entries in reverse in order to kind of scan backwards and recreate what the tuple actually is that we're looking for. And so the advantage of this log structured approach is that it has very fast writes. That to modify the database, literally all we do is append a new entry to our log. And so that's going to be very fast. Reads, however, may be potentially slow, this kind of reconstructing the log. There are a lot of tricks we might do to kind of compress or otherwise optimize our log for faster reading. But we would use something like these log structured pages if we have a database whose primary purpose is just to kind of keep a record of what happened, and it's rare that we would need to kind of go back and read a bunch of data, and it's to have this sort of very efficient kind of record keeping that we can go back and query if we need to, but the expectation is that we would not need to do that, very much. All right. So we have log structured, slotted pages. These are, and kind of for the databases that we're going to be thinking about going forward, it's typically this slotted page layout. All right, so that's the pages. Let's dive a little bit further and say, all right, what is actually going on inside of these individual tuples? How are they structured? and the tuples are basically just arrays of bytes. They're just some bytes stored on disk or in memory, and it's up to the database system to determine how to interpret how to interpret those bytes. And this is where the kind of the types that we give the attributes in our relational tables is going to be what is determining how the database system interprets the bytes stored there. And so there are kind of 5 major kind of categories or of attributes that we would have in tuples. So we might call data type. So we're going to have integers, and most systems will provide kind of different sizes of integers. If you need to represent especially big values, or you're only representing a small range of values and can save some memory, but these are just going to be the kind of 2's complement or other integer representations that are defined in the IEEE 754 standard. They're what you would get from C or C++, the kind of native integer types that are represented in hardware that the CPU has instructions for, etc. And these are going to be of fixed length. We also would have variable precision numbers, and variable precision is another word for floating point. These are also the kind of C or C++ float or real and SQL that are using the IEEE 754 floating point standard. These are the CPU has floating point instructions that work on these variable precision numbers. So this makes them efficient because the computer system has operations specifically tailored to this way of representing real numbers. However, these have rounding errors that if you say want to represent 0.3, you can't do that with a finite binary fraction exactly. So you end up with 0.2999998, and then so you get close but not quite. And so if your application is extremely sensitive to these small rounding errors, this is not going to be sufficient. So what you do if you need like very precise mathematical numerical representation, you would go with fixed point numbers, which say, all right, here is exactly how many decimal points to keep track of. They're going to kind of be a variable number of bytes based on the precision that you're going for, and these are going to be things like numeric or decimal in SQL, and these the database system will have to implement itself. That these kind of fixed point numbers, you're not getting them from C or C++, and so we can avoid all the rounding errors with these, but they will be slower to work with. The CPU doesn't have specific instructions designed to work with these, so it's a trade-off in terms of accuracy, but lower performance. And there'll be another demo from Andy Pavlo linked in the description around how these variable precision and fixed point numbers actually work in a database system. All right, a couple more data types. We have variable length data. And this is things like strings will be variable length, but there are other things that we might store in databases besides strings. Some cases we might want images or videos in our database, or some other sort of complex, like a JSON object, a kind of complex structured object. And so these will all kind of be variable length. Most database systems don't allow a tuple to be bigger than the size of an entire page, and so if you have very large data, the database system will do things like if the tuple is too big, it will have a whole separate overflow page for the extra stuff from that tuple. If these are like giant video files, you probably don't want them stored in the database at all, and there maybe all the database has is a pointer to some external file. And so this variable length data is kind of a big umbrella category, strings, but also kind of a lot of these other stuff. And lastly, very common that we would have dates and times in our database, and these could be like a timestamp of when a user last logged in, or the date some transaction took place. And underneath, these are typically stored as what's called Unix timestamps, which are the number of seconds or milliseconds since the Unix epoch began, which is January 1st, 1970. And so this is a standard way of representing a particular date and time, is just the number of seconds since January 1st, 1970. And so that's frequently, even if what the table has is, say, just like the date, underneath it's likely still the full timestamp, and just part of that is not being used for a particular time. All right, so we've kind of dived all the way down into pages, the disk as a whole, and then the page layout, and then what's actually going on inside these tuples with these different data types. Kind of now I want to kind of go the other direction and zoom out and ask, all right, what kinds of work would we want to do with our databases, and how does that influence our thinking about how the storage of that database should be structured? So we'll get rid of all of this stuff. All right, so I'm thinking about what kind of work that our database might do. We'll call these workloads, kind of some description of the kind of task or kind of operations that the database will be doing. And there's basically two broad categories that we're going to think about here. And we'll put them on an axis, on a graph. And we'll talk about the operations that workload focuses on, and then the complexity of those operations. And so we'll say, is this workload more involving writes? Is it doing a lot of modifications, updates, inserts to our data? Or is it primarily reading the existing data and not attempting to modify it? And then are these operations, are the individual operations relatively simple? Or are they tend to be more complex? And so the two main workloads that we're going to be thinking about, kind of one lives here and another lives here. And so we talk about online transaction processing, or OLTP, and that will live here. And OLTP is a situation where we have a lot of fast, short-running operations. So a lot of simple operations that operate on a kind of single entity at a time. And one way, an example of this might be the Amazon storefront. So lots of users interacting with the storefront, adding things to their cart, purchasing items, writing a review. But all of these, while there are a lot of these operations, they all involve just a particular user or just a particular product. And many of them involve kind of writing some update to that product, to some property of that user. And so that will fall under this kind of online transaction processing workload that emphasizes writes, though of course their reads are involved as well. But the emphasis is on writes, and it's a lot of simple operations. Our kind of contrasting is our online analytical processing, or OLAP, not OLAR, OLAP. And this is a kind of workload where we might have kind of long-running or more complex queries that are reading large portions of our database. And so here we're not ingesting new data. The data has already been collected, perhaps by an OLTP workflow. And then in an OLAP workflow, we're kind of reading a bunch of this data that's been collected and trying to derive kind of insights or new information. If you've heard buzzwords such as business intelligence or decision support, that often describes this kind of workload. And an example would, going back to Amazon again, an example would be, it wants to compute the 5 most bought items over a 1-month period for a bunch of different geographical locations. So this is not recording kind of new user interactions. It's not updating the database. It's reading this massive chunk of data across all these different locations. What were the items bought over the last month? Find me the 5 most bought ones. So this is kind of more complex than like add this item to a cart, and involves emphasizes reading data over writing it. And so there's also a kind of new a newer idea called HTAP. Really like writing R's for P's today. HTAP, and this is hybrid transaction plus analytical processing. It basically tries to be a combination of these two, that you want to kind of do these two in the same database. So these aren't kind of ironclad categories, just ways to think about what kind of work is being done. And another aspect that typically divides these two is that OLTP is concerned with kind of recent operations. You're kind of doing lots of ongoing updates, and so you might actually have, if you're an organization like Amazon that wants to do both of these things in kind of different contexts, you might actually have 2 different databases for that purpose. You'd have kind of one database for the OLTP that maybe just keeps the most recent 60 days of data, and so isn't trying to be this kind of long-term storage or record of everything that's been done. It's just kind of recent transactions. And then you have all the data in some separate sort of data warehouse type database, where you would run these kind of complex queries to get insight into what's going on. So we have these 2 models of workloads. So now we can think about how do these workload models influence our choice of storage model. So we're talking about storage model, we have a kind of assumed up till now what's called the NArea storage model. But I want to emphasize that our kind of relational model of databases doesn't require a particular structure of like where to put the different tuples or parts of tuples in our database. So it defines kind of this separation of the logical layer, our tables and the tuples within them from the physical layer, how we're actually storing them. So let's talk about this NArea storage model first. This says that the attributes of a tuple are all stored contiguously on a page. And that's sort of the picture that I had when I was talking about the slotted page layout, that all the attributes from a particular tuple are together in a chunk of memory. And so our NArea storage model, also called a row store, because the chunks of data that are stored contiguously together are the rows. Kind of each row, each tuple in our database is stored together. And so what this looks like is if we have our database, which I'll draw as this very sketchy cylinder. There are a bunch of pages within our database. And what's actually in a page under our NArea storage model is kind of each tuple is stored contiguously. So a tuple might have a header that describes kind of that has information on kind of the number of attributes or information about variable length attributes, where to find them, and imagine this is data for say a website like Wikipedia or Amazon that's going to be keeping track of things like a user ID, an account name, a password, and like a last login time that the user the user logged in. And in one of these pages, we just have kind of tuple number 1, tuple number 2, kind of all these same fields in each, and kind of a page of our database just contains the full tuples. And this is ideal for our OLTP workflow, because the kinds of things that we're doing under that workflow are inserting a new tuple into our database. And so we just like bring up the relevant page and slap a new tuple in there. We might want to kind of retrieve, we might want to update, someone logs in and we want to update the last time that they logged in. We're going to a page, we're grabbing out the tuple for a particular user and updating one part of it. And so this is nice because if a single kind of read from disk can bring in the entire tuple that we're looking for. And so this is going to give us kind of fast inserts, fast updates, fast deletes, and what it's not good for is if we want to kind of scan the data for a bunch of tuples that like match a particular criteria. So let's say in this we also had a column that was like the geographical location, some information about the domain or the IP address that someone is logging in from, and we want to run a query that's like how often have people from this location logged in over the last month. And so when we run that query, the data that we actually need is the login time and the location. But what we're actually going to, when we read the pages in from our database, what we're actually going to get is all this other stuff that we don't need for our particular query of like the number of users who logged in from Minnesota in the last month. We just want kind of login and location, but when we read in the page from the database, we get all this other stuff, and our buffer pool kind of gets cluttered with all this data that our query doesn't actually need. And so if we're trying to do queries like this, which would fall under this online analytical processing, this NArea storage model where we're kind of storing the entire tuples contiguously is not going to be the best choice. And so what we will want to do instead is to use the decomposition storage model. And so this NArea storage model is sometimes abbreviated NSM, or decomposition storage model, DSM. And the idea here is to do what's called a column store, which is, instead of storing each tuple contiguously in our pages, we want to store all the values for a particular attribute contiguously. So what this picture will look like is, again, we have our artful cylinder of a database, and it has some pages, and we can look, okay, what's inside this page, and this might be the login page, and we might have a ID page and a name page. And what this means is that inside this page, we just have all the login timestamps. So login from some tuple, from another tuple. We just have all the kind of login values across all the tuples together in a single page. And so this means that when we do a query like, give me the number of users who logged in from Minnesota in the last month, what we can do then is we can just get the page with the login values, the page with the location values, and we're getting just the data we need and none of this unnecessary stuff. And so this column store approach is going to reduce the amount of wasted work for executing these kind of analytical queries compared to this row store approach. And because we have a bunch of values of the same type all stored together as opposed to like a mix of values in a tuple, we can often take advantage of data compression techniques that kind of compress out a bunch of repeated information in terms of decreasing the size this takes up on disk. Of course, the disadvantage is for our kind of OLTP queries of, all right, update the login time for a particular user ID. Then we have to kind of go to the ID page and find kind of where and there, and that kind of might tell us kind of where then in the login page should we go to update that. And so these sort of point updates or deletes, we kind of have to do extra work to stitch these tuples back together. And so these are just two very different kind of approaches. Are the kind of database, when I say we've assumed this NArea storage model, it's because things like Postgres and SQLite are using this are row store databases. They're using this NArea storage model where they're storing the tuples together. Whereas these column store, there is a fairly long history of this, but kind of it's become more and more common to be able to do this sort of column store, and kind of now modern enterprise systems often support both the kind of row store and the column store. You can kind of tell the database how to store specific data. All right, so that's what I have for you about database stores, kind of zooming way in and also zooming out. So I hope that Project 1 is going well, and I look forward to your questions on that and on the storage model.
Round 1. Oh! Fight!
Oh!
Ooh! KO!